Imagine, if you will, you've never played basketball. No one ever told you the rules, and all you could do is watch. Well, if you think about it, that's kind of the way it is in nature too. No one tells us the rules. All we've done the past few thousands of years is watch and try to figure out how to play. In chemistry, since August, we've been learning some of the rules by which these atoms play. We use the rules of stoichiometry to predict how much mass we can create in a reaction. We've used the rules of thermochemistry to predict how much heat will be transferred in a reaction. We've used the rules of kinetics to predict how quickly atoms will react, and we've used the rules of equilibrium to predict just how much reactants and products we'll have at the end. But yet, we're still missing a key idea, and that could be the biggest one of all, and that is, what's the point? Why are we even playing this game? What's the object of this game anyway? Well, this is where the rules of thermodynamics come into play. For example, why do acids and metals react with each other, but sugar and metals do not? Why do hydrogen and oxygen react to make water, but hydrogen and water do not? Why does candle wax burn to produce H2O and CO2? But the reverse process does not happen. H2O and CO2 does not form candle wax. These are all questions we will answer in thermodynamics. As we work our way through this lesson, though, keep in mind that thermodynamics only says which reactions will and will not happen. It doesn't say how quickly they'll happen. That's the job of kinetics, which we've already covered. And so an outline of what we're going to talk about in the next few videos is, first of all, spontaneous processes. What does and does not happen. Then we'll move on to entropy, a word some of you may be familiar with, which is simply maximizing disorder. Then we'll go to free energy, sinking to a new low, and then lastly we'll tie it all in with our equilibrium stuff, relating thermodynamics to K, Q, and equilibrium. So let's go and get started with these thermodynamically favored processes. That's a fancy way of saying spontaneous. Now it should come as no surprise that the word spontaneous means something slightly different in science than what it means in the everyday vernacular sense. In the everyday sense, if someone is spontaneous, that means that someone kind of does things on the spur of the moment without really thinking about things. Let's go bowling, they might say. Let's go to the movies. Let's study chemistry. In science, however, a spontaneous process is not quite the same thing. It's something that happens. It doesn't necessarily happen quickly, it doesn't necessarily happen right away, but it does happen. Let's look at some things that are spontaneous, that just happen by themselves. A rock, for example, will roll down a hill. That's a spontaneous process that does happen. You do not see, however, a rock roll up a hill. That would be a non-spontaneous process because it doesn't happen, at least not by itself. Something else that just happens is if you light paper on fire, it will produce CO2 and H2O. That is a spontaneous process. What you do not see happen, however, is CO2 and H2O combine out of thin air to rain down sheets of paper. That is not a spontaneous process. You would be surprised if that happened. Something else that's spontaneous, that just happens. If you drop a deck of cards, the deck of cards is going to get mixed up. It just happens. What does not happen is if you drop a deck of cards and the deck orders itself in 4 suits from ace to king. That does not happen. That is not spontaneous. You would be very surprised to see that. Something that does happen is the Cardinals tend to lose, and that would be a spontaneous process. Non-spontaneous example of that would be Cardinals winning. Note, until last year, that slide always said Cubs lose and Cubs win, but some things have changed since then. Next up, things that happen. Water vapor will condense at 100 degrees Celsius. If you start with water vapor at 210 degrees Celsius and cool it down, it will remain a vapor until you get to 100 degrees Celsius. Then it will condense into a liquid, at least at room pressure. What you do not see happen is water vapor does not condense at 200 degrees Celsius. That just doesn't happen. That's not spontaneous. And lastly, if you have purple dye, for example, grape Kool-Aid, and you mix it in with water, that purple dye will spread throughout the water. That's spontaneous. That happens. What you don't see, however, is if you're drinking that glass of Kool-Aid, all the purple dye does not go into one corner of the glass. That would be surprising. That does not happen. That is non-spontaneous. So, a spontaneous process is something that just happens. You'd expect to see that. That's a meh kind of reaction. On the other hand, a non-spontaneous process, that would be surprising. You would be surprised to see that happen. Wow is what you'd say. if you saw a rock roll up a hill, or sheets of paper form out of thin air. So things that happen without help from an outside energy source are said to be thermodynamically favorable, or a shortcut is spontaneous. On the AP exam, they prefer the term thermodynamically favorable because the word spontaneous, as we said earlier, has different connotations in the real world sense. On the other hand, something is thermodynamically unfavorable if that process requires a sustained input of energy from, for example, you or something else. Or you could simply say that process is non-spontaneous, but again, the AP exam will use thermodynamically unfavorable. Now, it's very important to keep in mind that just because something is not spontaneous does not mean it's impossible to happen. It can happen. Rocks do roll uphill. It's just that they don't roll uphill by themselves. You have to force that rock uphill. You have to use some of your own energy to make that rock go up the hill. Similarly, a deck of cards is not always going to be disordered. You can order a deck of cards. It just takes time and energy on your part to do that. And you can separate purple dye. It just takes a little creativity and a little input from you to make that happen. So again, a spontaneous process happens in nature just by itself. A non-spontaneous process could happen. It just doesn't happen very much. And if it does, you're going to have to use some of your energy to make it happen. To really explain the idea of spontaneity, we have to address something called entropy. Entropy is a fancy word that some of you may have heard already, and we're going to define it a little bit better though. Entropy is kind of an abstract term, and you can get pretty technical with it, but we're not going to. We're going to keep it pretty non-technical. In fact, you can basically think of entropy as simply disorder, or messiness, if you will. A slightly more technical definition of entropy would be this dispersion or spreading out of energy or mass. And so let's take a look at a burning candle, for example. If you have a burning candle, the wax consists of carbon and hydrogen bonded together. When you light it, that carbon and hydrogen react very readily with the oxygen in the air to form carbon dioxide and water vapor. That carbon dioxide and water vapor then spreads throughout the room. So here we see a spreading out or dispersion of mass. All that mass that was in the candle initially, all those carbon and hydrogen atoms, are now spread throughout the air in the room, and you can breathe it in, breathe it out, and it fills the room. So we have a spreading out of mass. In that sense, the entropy change of the burning candle has increased, has become more positive. You have more entropy in the carbon dioxide and water vapor spread throughout the room than what you did in the candle to begin with. But we can also look at this in terms of energy, too. For example, in the candle, the energy was concentrated in the form of chemical potential energy between the carbon bonds, the carbon and hydrogen bonds. After it's burned, however, and reacts with oxygen, now you have chemical potential energy in the form of carbon-oxygen bonds and CO2 and hydrogen-oxygen bonds and water vapor, but you also have a release of energy as well. You have heat that's released and light that's released. This heat and light is also spread out throughout the room so that the energy that was once contained in the candle now fills the room. Eventually, when the candle goes out, all the energy of that candle will have dissipated into the room and spread out. And so again, we have a positive entropy change when we burn a candle. So if you were to choose any letter of the alphabet to represent entropy, you would obviously choose the letter S. I guess E was taken. Think of it as spontaneous, perhaps. And units are joules per Kelvin. Again, kind of an awkward unit. Probably doesn't mean a whole lot to you. If you really understood entropy and the technical definition that we skipped over, it would make a little more sense, but we'll just move on for now. Often it's useful to think about changes in entropy. In fact, we don't deal with straight-up entropy much. It's usually the change in entropy, just like enthalpy. And thus, instead of seeing just S, usually we see delta S instead, where delta S is the change in entropy of a system. We can also consider the entropy change of just a system, or the surroundings, or the universe. If you add the two together, system and surroundings, you do get everything the universe. So your system may be your beaker or flask, the surroundings may be you, the room, the trees outside, whatever, and the universe is all of those things put together. Now, for sign conventions, recall that entropy is kind of like disorder or messiness. And so if you get more disordered, more messy, more spread out, then your entropy change is positive. Delta S is positive. So again, disorder increases and things get messier if your delta S is positive or your energy is spread out. On the other hand, if things become neater and energy and matter is condensed, then you have a negative change in entropy. Delta S will be negative. The whole reason entropy is important is because for all spontaneous processes, every single thing that you can think of that just happens by itself, the entropy of the universe will increase. Delta S is positive. This is known as the second law of thermodynamics, the first being the conservation of energy, and it says that the universe is unwinding into a more disorganized state with less and less concentrated energy sources. So, for example, astrophysicists believe the universe is about 13.5 billion years old. And as you may recall, most astrophysicists believe the universe started out as this really, really tiny pinpoint of matter. Then something called the Big Bang happened, and all this matter was spread throughout the universe and continues to spread throughout the universe. Not only that, but all the energy is also continuing to spread throughout our expanding universe. And so entropy is increasing as this matter and energy is spread into larger and larger volumes, and it becomes more and more spread out.